Now the derivative has quite a few different names and there's a lot of different ways of writing it. Now today we're looking at what we call dy dx notation. Now you'll notice dy dx, it looks like a fraction, but instead of saying dy over dx, we tend to just say dy dx. Now the derivative can be written as dy dx, this is the new one we're learning today. We've already seen f dash x. It can also be written as y dash, so we've got a few different ways of expressing it. Now which one do you use? Well, it depends what you're given as the actual function, and you want to keep your notation consistent. So if you're given a function f of x and you want to differentiate it, you tend to say f dash x equals whatever you get. You keep that with the one that it goes with. Y can be differentiated into either y dash or dy dx. Now why would you use different notations? Well, they have different advantages. If you're finding, say, that you have a curve like this and you want to differentiate it, so you find f dash x, which would be this. The handy thing about the f of x notation is that if you want to then find a certain spot on the curve, let's just say you're saying, well, when x equals 2, what's y? You can say, well, I'll just find the function of 2, and away you go and sub 2 in. You don't have to write when x equals 2, y equals, you can just write f2, and it's very quick. And mathematicians love things that are quick and time-saving. At the same time, you can also say, what's the gradient when x equals 2? And you could find f dash 2 just by subbing a 2 into this one. So you don't have to go through all that time saying, when x equals 2, dy dx equals blah, blah, blah. So the f notation is really quick. That's its advantage. And you can easily sub something into it without having to write long-winded explanations. What's the advantage of the y dash notation? Well, if you've said that y equals something or other, then y dash equals the differentiation of that, it's very quick to write. So that's even faster. The disadvantage over the f of x is that if you want to sub something in, you'd have to say when x equals something, y dash equals, you have to write all that out. Whereas the f dash x notation allows you to just sub a number straight in. So the y dash, quick to write, but a little bit clunky when you need to sub things into it. Now, what about dy dx? That's the one that we're learning about today. Well, dy dx, it looks like a fraction. So that kind of keeps consistent with what we understand that the gradient actually is, because we know that the gradient is a fraction, isn't it? It's rise over run. Now, dy dx both is and isn't a fraction. It sort of behaves as one, even though it's not strictly a fraction. And that's where its advantage comes in, is with its meaning. It also has an advantage in that if you want to find dy dx, which we'll see means a change in y over a change in x, then you can actually say, well, that means I'm going to differentiate y with respect to x. This d means I'm going to differentiate. This tells you what to differentiate. The d on the bottom tells you what to look out for, and then you look out for these. So this really means differentiate y, looking out for the x's and differentiating those as they come. Now the advantage of this is that if you've got a function, let's say y equals, we'll just make one up, and you want to say, well, therefore dy dx equals, and you can go ahead and differentiate that thing. That notation is perfectly adequate. And often we'll ask you a question where we say, if y equals a certain thing, find dy dx, and you can go ahead and do it. But if we're differentiating y with respect to x, and y is equal to a certain number of things, this notation allows us to ask you the question a different way. If you can differentiate y with respect to x, and y equals all of this, you're basically differentiating x cubed plus x, 2x in this case, and you have something that looks a bit awkward, but it looks like this. Now this means the same thing as dy dx. We've just subbed what y was in there. Now it's not often written this way. It's more likely to be written so that we have the dx and the fraction line over here. And this terminology now gives us an action. To ddx something is to differentiate it. So this allows us to ask you a question like this. Perhaps in an exam paper this might be question 5, and it will just say ddx this. you then don't have to write what y equals or whatever x equals. You can then go ahead and differentiate the thing in the brackets and just say, oh, it's 3x squared plus 2. And it's a nice simple way of actually just differentiating something because this is the action telling you what to do. So that's one of the advantages of the dy dx notation. Now, how do I understand what's going on with it? Well, let's look at this picture. It's really similar to the one that we looked at with f of x. I've labelled 2 points, P and Q, that are on some curve. Now, if this is x, this random spot here at P, then its corresponding y value will just be y. Then if we say, all right, we'll make another point on the curve, we'll call it Q, and we'll gradually bring it closer and closer together so that it's very, 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 very close to P. Now, this symbol, delta, written with a sort of squiggly line like that, means small change in. So if I've got x and then I've got a very small change in x, then this point over here is x plus a very small change in x. And correspondingly, if I've just made a very tiny little change in x to move me along to here, then correspondingly I must have made a very small change in y to bring me up to the y value of q. So this will be y plus a very tiny little change in y. Okay, when we go to find our gradient of PQ, we can say it's rise over run. And the rise, if we drop a line down and across to see the gradient of this PQ, the rise is clearly a change in y, and the run is a very small change in x, and we can write that as delta y over delta x. Now, you might notice this delta with the squiggly line, it looks a bit like a D, and it even stands for delta, which starts with D. And it's not a coincidence, that's why they've picked the letter D. But it's important to note that dy dx is not the same thing as delta y over delta x. There's an important distinction, and here's where the definition comes in. Dy dx is actually the limit. Remember, we need to always take a limit. With our f of x notation, we made the limit as h approached 0, and we call this h. So we need to take the limit as the change in x becomes really, really tiny. In other words, as it approaches 0. And we need to take the limit of this. So we rewrite our change in y over our very small change in x, and that is what dy dx is. This one is a fraction, definitely. This one looks like a fraction because it's written with this fraction line, which actually allows us to treat it like a fraction in a few tricky ways, but it's not strictly a fraction because it's actually a limit as change in x becomes very, very close to 0 of this, which is actually a fraction.